All right, how's everybody doing? Pretty good. All right, so lots of things to go over today. So midterm grades are posted with comments, and I put all the grades in the first question. So see the comments for where where points came off for particular problems, because most of the problems are recorded in Canvas as a 0, but the comments show where the deductions were. It seems like it was a bit of a long midterm. A lot of people took the full time. Some people expressed running out of time. So the final exam you'll have 2 hours for, so hopefully time won't be as big of an issue on the final. I threw in a curve. I don't normally throw in curves until the end of the course, but I threw in a 10-point curve on this test just because it felt like a lot of people really kind of ran out of time, and I think people probably got a little freaked out about the time because 50 minutes isn't that long, and if you start working and suddenly you've only got 20 minutes left, it's hard to work efficiently under that kind of pressure. So anyway, there's a 10-point fudge factor on all of the scores, so if you add up your points, it should be off by 10. Despite that, don't panic too much about the numeric aspect of your midterm grade. Okay, the final exam is more important in terms of performance in the course. What I want you to take from the midterm, though, is if there are concepts that you're unclear about, if there's things you thought you understood but you don't, or if there's things that you're kind of rusty on, and given enough time you can do them, but under time pressure they become confusing and so on. I want you to take from the midterm, what things you should work on more, what things you should practice, what things you should ask me about to try to be prepared for the final exam, to run into those kinds of issues. So a lot of what we're doing for the rest of the course and a lot of what you'll see on the final exam will involve the kinds of things that you were doing on the midterm, right? Writing pieces of code, setting up registers, tri-state bits, things like that. So you still want to be clear on those, even though we're moving on to other subjects. You want to make sure that you're good on those, because those are the fundamentals. Those are the things that we'll use to build most of everything else we're doing. So don't get too panicked about the grade, right? Everybody in this course is still able to pass the course with at least a C if you do well on the remaining material and on the final exam. But if you feel like your grade was really low and you're worried about it, use it as a chance to see what you should brush up on, what you should try to get more help on. Okay. I would like to talk about the midterm first. I want to go through the questions and answers and talk about some of the pitfalls I saw. And then I want to talk about the homework, and then talk about any questions related to Lab 4, which was the interrupt lab you just turned in. And then I want to look at timers in more detail. We talked about the basic concept for timers. I want to look at timers inside MPLAB and actually see how some of these things work. Possibly look at interrupts inside MPLAB, and then go ahead and talk about Lab 5. I'm probably going to run over the regular 2 hours today. I'll probably go until about 2:15, because I want to make sure that we talk about this stuff and that people can ask questions along the way and so on. So let's start with the midterm. So question 1 was our old favorite, which is converting instructions into machine code and expressing them in both binary and in hexadecimal. So a good number of people did not write these out in hexadecimal, they only put them in binary. So you want to see both of those. All right, so let's pick on this first and last one, and then let's pick on the second one. So this first one is saying increment file register hex 26. All right, things to think about. Your destination bit is going to be a 1. Right, all of these byte-oriented instructions, you get to specify, should I put the result back into the file register, that's a destination of 1, or into the W register, that's a destination of 0. The default is 1. If you want to go into the W register, you say comma 0. What this bit is specifying is the destination bit. Okay, the next thing to think about is the access bit. And we did an exercise on access bits, and remember, whether we set the access to 1 or 0, we're going to end up going after file register 26. So access bit can be 1 or 0 in this case. If it's a 0, it says use the access bank. We sign extend this, which is just 26. If A is a 1, we use the bank select register, which is a 0. This is still going to be 26. So this is one of these cases where the access bit doesn't matter. So now you go and you look at the data sheet. And you look for increment file register, and it's got this pattern 0010, 10DA, and then 8 Fs. All right, so the destination bit's going to go right here, the access bit is going to go right here, the file register is going to go right here. You didn't catch that. Destination bit goes here, access bit goes here, the file register comes from the operand, that's hex 26. So this thing codes in binary as 0010, 101 for the destination bit, and then this can be a 1 or a 0. And then the file register is the hex version of 26, which is 0010, 0110. And if you convert that to hex, that's a 2A26 or a 2B26. So either of those would be correct. Now this last question says increment file register 26, comma 0. If you want the destination bit to be 0, this changes to a 0, and so this becomes a 0. And now your instruction codes up as either 2926, or if this is a 1, 2B, or if this is a 0, 2826. Right? Exactly the same opcode, exactly the same operand, single bit changes in your machine code, that destination bit. All right, let's look at B, because B is where the access bit is going to come into play. And first thing you have to do is you have to figure out what the address of port A is. So go back to your data sheet. And at the very end, we have our special function registers, and port A is F80. So this instruction is actually saying clear file register F80. Remember, every instruction is 16 bits. We can't put in 12 bits worth of address information. The clearF instruction is not big enough. So clearF is 16 bits, just like increment F. And it looks like this. 0110, and then 101, and an access bit, and then 8 bits of file register. All right, 0110, 101, and then the access bit. Alright, so back to our access bit exercise. What is the access bit here? If we set A equal to 1, it's going to take this and it's going to add zeros on the end. So if we put in 80, it's going to try to clear file register 080. If we set the access bit to 0, that uses what's called the access bank. And remember, if we say clear file register 80, it will sign extend that. Now 80 hex looks like this. And so if you sign extend that, if you add 4 more bits, you're going to add 1s. And that's going to be F80, which is the address we actually want to clear. So the trick to coding this instruction is to say, let's clear file register 80, but set the access bit to 0. And it will sign extend the 80 to an F80. So we put a 0 in here, and then we put 80 hex for our file register. And so this is the instruction 6A80. That's how we code up clear file register port A. And if questions come up while we're going through this, go ahead and ask. Let's do the move literal, because literals are a little different too. Move literal W hex 55. So find your move LW. Well, it's in the literal section down here. Move LW, and it codes up as follows: 0000, 1110, and then whatever literal constant you want to move, your 8-bit constant. So the literal we want to move is just 55. So there's a 5, there's a 5. And the opcode is unaffected. So this codes up as hex 0E55. Detail point, make sure you put in that 0. If you're trying to write a 16-bit number in any kind of computer science context, put in the leading zeros. Right? If you give someone an opcode of instruction of E55, they're going to look at you funny. So make sure you express it as a 16-bit number. And there's no wiggle room here. There's no destination bit. There's no access bit involved, because we're not dealing with file registers. We're dealing with just an 8-bit value. You notice on the increment file instruction, we got to specify a destination bit and an access bit. Well, the access bit we need because we're using a file register. We might be using, one of these special function registers. The destination bit is because when I increment this, do I want the result to go back into 26 or into the W register? We have to specify. But there's no destination bit on the clear instruction. It would make very little sense to say clear file register port A, but put the result into the W register. Because that's just saying put a 0 into the W register. And if you want to do that, you could just say clear file register W reg. Or you could say move LW 0, which would move a literal 0 into W, and both of those would clear it. So there's no destination bit in this instruction, right? You can always come into your data sheet, table 20-1, and see exactly how each of these instructions is coded. And if you see something in here that doesn't make sense, think about it, right? And or ask about it. Because it can really sort of like tie lots of things together, thinking about why these decisions were made in the architecture. All right, so that was question 1, which Canvas called question 2. Question 2, your goal is to repeatedly read a 3-bit number from port B, bits 2 through 0, add a 2-bit number from port B, 5 through 4, add these together to get a 4-bit sum, and if that sum is exactly 6, set port A bit 0 equal to 1, otherwise set port A bit 0 equal to 0. Alright, and this is similar to the lab you did, with a few differences. So we're reading from port B. It's always an 8-bit register. And the first number that we're reading from is from bits 2 through 0. So this is your first num. And the second number you're reading comes from bits 4 and 5. So this is bits 0, 1, 2, 3, 4, 5, 6, 7. So this is your second number. Alright, so most everybody nailed the bit masks. That was awesome. Okay, bit masks are key, and people seem to be doing well with those. So you have to set this thing up, right? So 7F goes into addcon 1. So I'm writing pseudocode now, but if I write this, most people, I assume, know that they can say move LW 0x7F, move WF addcon 1, right? We've done that a bunch. You're going to use these bits as inputs. Well, by default, these things are inputs, but if you wanted to be explicit, right, you could put 0, 0, 1, 1, 0, 1, 1, 1 into tris B. Or, you know, you could just put all ones into tris B. Because we don't usually make pins outputs unless we plan to, you know, hook something up to them. So inputs are safe, and that's the default condition anyway. But we're going to output a sum. We're going to output a flag on port A, bit 0. So we need to set bit 0 of port A to support output. So we could do something like put this bit mask into tris A. Or we could just say bit clear file register tris A, comma 0. So just take that least significant bit of tri-state A and set that to a 0. That makes the least significant bit of port A an output. So that sets us up to do our output. And then it's kind of business as in the lab. Make a loop because we're going to do all of this again and again. So move F, port B into 0, and the W register with a literal. Right, so that throws away all of these bits, makes them all zeros, and it just takes whatever's in these 3 bits and preserves them. And then maybe save that into num1. So you have to declare num1 and num2 somewhere up front. And then move port B into the W register again. And it with a bit mask to get these 2 bits. Save that in num2. But num2, our number is going to be sitting in these 2 spots. We really want it in these 2 spots so we can add it to num1. So do a swap. That brings these 2 bits over to here. There's also rotate instructions. You can rotate a register, and it basically means move all the bits down 1 spot or move all the bits up 1 spot. We can rotate right, which shoves everything that way. We can rotate left, which moves it that way. So it turned out my number started at bit position 4, so a swap brings it exactly over here. But, you know, if my number was these 2 bits over here, I could swap right 1, 2, 3, 4, 5, 6 times. I mean, rotate right, or I could rotate left twice. So there's options. But anyway, do something so that num1 and num2 are comparable to each other. And now we can do something like move num1 into W, add W to file register num2. And it's okay if we change num2 here because we're loading num2 every time that we run through this code. But, you know, we could also put this in the W register. If it's a habit, it doesn't matter. But if we put this in the W register, then we want to know if the sum is equal to 6. So easiest way to do that, just subtract 6 from the W register. If the result is 0, then that sum was equal to 6. So branch of 0, sum is 6. Otherwise, the sum was not 6. And so the instructions say if the sum is 6, set that bit to a 1, otherwise set the bit to a 0. Okay, the sum was not 6, so just bit clear, port A, bit 0, and then go back to whatever we called this loop. And down here is our label for sum is 6, and here we'll bit set port A 0, and then branch to loop, and then your end. So it's a modification of your earlier lab. So issues I saw in here, not setting up ADCON 1, not setting tris A bit 0 for an output, not using the swap, trying to use the swap on port B. We can't do that, right? You can't swap at port B unless you put the result into something like W. If I try to swap port B, I'm saying take whatever switches you have connected to these pins and move those switches over to here, which makes no sense, right? You would need to physically modify the universe somehow, because these are inputs. And if this is a 0, it's because there's a switch there connected to ground. Well, if this is a 1 because it's connected to 5 volts and I say swap F port B, how in the world is that possibly going to change the voltage on this pin to 5 volts if it's already connected to ground? Right? These are inputs, and a swap is actually a read, modify, write. So we can read these bits, we can modify them, but we can't write them back to port B, because port B, these bits are input bits. So copy it somewhere else before you try to do a swap. You have to loop back to the top because the problem says to do this repeatedly. If you don't put a branch somewhere to go back up to the top, your code will fall through and execute random code from the PIC's memory and eventually generate an error. We'll talk more about this in question 5, but when you're doing these conditionals, which are saying, you know, if this is equal to 6, then do one thing, otherwise do something else. If, for example, you don't have this branch here, what happens? Okay, we added num1 and num2, we subtracted 6. Let's say the sum was not equal to 6. So it's not going to be 0, we're not going to take this branch, so we're going to clear bit 0. So far, so good. What's the next thing we do? We set bit 0. So bit 0 is now blinking on and off really fast because the sum is not 6. And that's not what we want. If the sum is 6, turn the light off. Turn off bit 0. And so we need to make sure that if we're not planning to do the sum is 6, we somehow don't fall down into this code. So throw a branch in here to either skip over this stuff, or in this case, just go back up to the top of the loop. So you'll see notes I made saying things like your else always happens. That's what I'm referring to. And we'll talk more about that in a minute with question 5. Make sure your bit masks are correct. I didn't take off if your bit mask was off by 1 bit position. But you know, it helps sometimes to draw a picture of the port and number these and draw your bit mask, you know, lined up with that. And then carefully convert that to hex or just use it in binary. So be careful about bits. And you know, even though for some reason we like to clear port A in the beginning of our programs to put them into a known state, that's not like a thing, okay? We don't in general just clear port A for kicks. And so I saw some code which at the beginning of the loop always cleared port A, and then if the sum was equal to 6, it set the bit equal to 1. And there again, your bit 0 is toggling, it's oscillating back and forth, and that's not what you're supposed to do. If you clear port A right in the very beginning before your loop, that's okay. That's putting things in a known state. But don't clear a port bit unless your intent is to set that bit to 0. Right? And so when we're inside our loop, our main program, and we're supposed to be doing something very specific, which is if the sum is 6, set it to this, otherwise set it to 0. If the sum is 6, set it to a 1. Don't set it to a 0 and then a 1. Right? So that's just a detail. All right, question 3. These were a short answer. How many general purpose file registers are there? 256. They go from 00 to FF. All right. There's special function registers, and there's actually 128 of those, and they go from F80 to FFF. But general purpose file registers, all right, that's that 8-bit operand on these byte-oriented instructions and so on. And we've said you can put any value in here that you want. You can use any 8-bit number. So from 00 through FF, that's 256 file registers. There's 256 8-bit numbers. There's 256 combinations of 8 ones and zeros. There's a lot of ways to think about this. If you've done CSE 215, you're rolling your eyes right now. So 256 file registers, general purpose. How many bits do most instructions require? 16 bits. Okay, you can count them on the data sheet. Most of these instructions, 16 bits. They're even labeled 16-bit instruction word. The exception is things like call, which uses 2 words, 32 bits. But most of these 16 bits, or 2 bytes. Okay, question C. If you want to read from bits 1 and 0 and write to bits 2 and 3, how would you set up your tri-state register? And this is port B. Well, let's draw port B. All right, we want to read from bits 1 and 0. So those are inputs. And we want to write to bits 2 and 3, so these are outputs. And these we don't care about. So our corresponding tri-state register if you want an input, put in a 1. If you want an output, put in a 0. And these we don't care about. So an acceptable value would have been 3. Or you could make these 1s and it could be, you know, F3 hex. But these 4 bits have to be 0s there, 1s there. Alright, what is the address in hex in program memory of the first instruction to be executed when you first power up the PIC processor? 0. Okay, it always executes the instruction at location 0 no matter what. That's the power on reset vector. It does not matter if you write code and your first statement is org 100. Right? Org has no effect on how the processor starts executing. Org says, where should I take the 1s and 0s for the following instructions and put them into program memory? Where should they go? But when you power on a PIC, it always starts with address 0. Which is why if you don't have an org 0 statement somewhere in your program, you're going to get unpredictable results. Alright, so PIC processor always starts from address 0. And then E, describe briefly any significant difference between branch and goto. Well, there's a few options here. Branch takes 16 bits, goto takes 32 bits. Okay, goto is probably slower because it takes more bits. Branch can only go to locations that are nearby. Goto can go to anywhere. That's what we use those extra bits for. Goto can go to anywhere in the megabytes of program memory. Branch can only go plus or minus a few thousand locations. Branches are relative. Gotos are absolute. If you take the machine code for a branch and you move it somewhere else, if it used to jump 5 instructions forward, it'll still jump 5 instructions forward. Gotos code into the instruction an absolute address. And they'll always go to that address no matter where they're sitting in memory. So they're not relative branches, they're absolutes. So any of those would have been good answers. Not so good answers were things that talked about calls and returns, because returns have nothing to do with branches or goto. Answers that talked about gotos going one place and branches going 2 places, well, a conditional branch might jump somewhere or fall through, but just a plain branch instruction always branches somewhere. It's almost exactly like a goto, except for a few differences, like the ones we just named. All right. Coding of instructions. So for what it's worth, I posted a video this morning. It's on the 270 channel. It is long and it is boring, but it is worth spending time if you're trying to get better at assembly language programming. The topic of the video, which is like 45 minutes long, is being able to take code for instructions like these and load them into MPLAB and see exactly what they do. And the point of making this video is to illustrate how you could practice assembly language programming using MPLAB. So you can take a problem like this, you can make up these problems really easily, right? And you can write assembly language code for it. How do you know if your assembly language is correct? You don't need to guess. You can actually go into MPLAB, you can single step through the code, you can look at everything that's happening, and you can tell exactly if your code is working or not. And if it's not, you should be able to rerun it and see exactly where it goes wrong. I can't stress enough how important a skill this is. Okay, it's one of the 3 pillars that I claim make an excellent programmer. That's the ability to debug efficiently. And if you just have to write code and it works or it doesn't work, it's not a lot of fun. Right? You write it and you're not sure if this is correct and so on, or you turn in a homework or a lab, you don't know if it's right or not. If you can actually go through and see this stuff working step by step, it not only lets you know if the code's right or not, but it really helps you understand better what's going on. Okay, we're going to do this with some interrupt code and with some timer code later on today, and hopefully that will exemplify some of this. But there's also this long video that I posted on YouTube on the 270 channel. Alright, so let's look at some of these. If number equals 0, set num equal to 1. And these, were homework questions, different specifics, but this was a batch of homework questions that we went through last week. So if num equals 0, then num equals 1. Alright, we need to test the value of num. Easiest way to do that is a move F. You can move num into itself, or you can move it into the W register. Makes no difference. If you want to use the W register for something else, just move it into itself. Or, put in the W register out of habit. Okay, this updates the status bits. If it's equal to 0, we want to set num equal to 1. So there's a few ways that we can proceed. Branch if 0, set num. Otherwise, branch to done, set num. Move literal value 1 into W, move W into file register num, and then here's our done. Okay, check the flow paths. Move num into itself or into W. If num is equal to 0, it will branch down to set num, put a 1 in W, put that into num. We've done num equals 1. If num is not equal to 0, it will not do this conditional branch. So we say it falls through to the next instruction, which says branch to done. Okay, again, most common error I saw was not having this in the middle. So move num into itself. If it's 0, come down to set the num. Otherwise, what's it going to do? It's going to fall through, and it's going to put a 1 into num. So this code, if you don't have this blocked out statement here, will always set num equal to 1. So you got to make sure you skip over it if that's what you want to do. Okay, a different way to do this is think not negative logic. We can say if number is not equal to 0, let's go to done. Otherwise, put a 1 into W, move that into num, and then here's our done spot. Since the condition says do something if this is 0, some of us tend to think about branching on 0 initially. But if you think about it a little beyond that, right, we can say, well, if it's not 0, let's not do this. So we can do a branch if not 0, done, or skip, or something like that. Okay? Any labels that I use, you got to define those in here. Don't just assume that the assembler knows where you want it to go. It's not that smart. All right, and this will not work either. Okay, when you put an end in your program, everything else disappears. In fact, if you have anything else, you'll get a warning or an error from the assembler. When you say end, it means there's nothing else in my input file. And if you see anything else, something is wrong. So we don't want to do that. You want to branch around. Return won't work, right? Because this doesn't say if num equals 0, then return. Or if num is equal to 0, num equals 1, else return, right? Return does something very specific. It's not just something we put at the end of a chunk of code. It says, I was called from somewhere, go back to the line after where I was called from. Okay, this is so much minutia and detail and fine print, right? Because you're talking to the transistors, the AND gates, the OR gates. You're talking to the hardware, and it's not very smart, right? You've got to really, really spell everything out in excruciating detail, and you've got to be absolutely precise. And if I put a return in here, it will do what? It will go to the stack, it will see what's on the top of the stack, it will pop it off, and it will jump to that address. And if the stack is empty, it'll set a flag saying something went wrong, and it'll reset the processor and go back to instruction 0. That's what it thinks I wanted it to do. Alright, question 2. If num is not 0, then set num equal to 0. So again, move num to set the status flags. And I'll do the direct version. Branch if not 0, set num. Otherwise, branch to done. Set num just has to say clear file register num. And then here's my done line. Negative logic, branch if 0 done. Clear file register num. And then here's done. So same idea, same comments. Don't forget that. Otherwise, if it's not 0, we'll set. Otherwise, we'll fall through and we'll still end up at set. And in either case, we'll clear num 0. All right, if num1 equals num2, result equals 1, else result equals 0. All right, how do we tell if two things are equal? Let's see if their difference is 0. Okay, so here we do need to take advantage of the W register, so we'll move num2 into the W register, subtract the W register from file register num1, put the result back in W. Do not change num1. Okay, this statement does not say anything about change the value of num1. It says compare the value of num1 to the value of num2. It doesn't say modify num1. But if we don't put this comma 0 here, this will set num1 equal to num1 minus num2, which is not what we want to have happen. So we subtract, we store the result in W. We don't actually care what the result is, we just care is it 0 or not. So let's check the status bit. So branch of 0, I'll just make a label called equal. Otherwise, I'll make a note that they were not equal. Well, if they're not equal, what should we do? We should clear result. So clear file register result. And I can't just put my equal down here, because if I do that, once I clear the result, I'm going to go ahead and execute the code that'll set result to 1. So let's skip over this now. Let's branch to done. And then equal, we'll say move a 1 into W, move W into result, and then here's done. If this is not making sense, let me know. Right? It's the same thing over and over and over again. Now, if you're writing, you know, thousands of lines of code, you can't call all of these labels done and equal, right? Labels have to be unique. So you can come up with a more meaningful name, right? Or, you know, you can call it equal 1, equal 2, equal 3, done 5, done 17, right? But there's nothing magic about these words. They're just labels that I'm using. Because to me, this is where I'm going when my arguments are equal. But you can call them anything you want. Don't start with a digit, though. They got to start with a letter, usually. All right, and then if num1 plus num2 equals 0, num3 equals num3 plus 1. So that's this fourth question here. And that's really the same thing, right? Take num1, put it into W, add num2, save the result in W. And then branch if not 0, done. Otherwise, increment file register num3. So really nothing special, nothing significantly different there from question C. And then question E, if num1 equals 5, num2 equals 0, else num2 equals num1. So the only real difference here is the literal. And maybe the num2 equals num1. All right, how do we tell if a number is equal to 5? Let's do if num1 minus 5 is equal to 0. So let's put num1 into the W register, and then subtract the literal value 5. So now W is equal to num1 minus 5. If you look at your data sheet at these literal instructions, they don't take a destination bit. Right? The destination bit lets us specify when we increment, for example, should the result go back into the file register or into the W register. There's no file register involved with these. So there's no destination bit. When we add something to W, the result always goes back into W. So you don't need to do a comma 0 after here. I didn't take off for that, but several people did that. So subtract a 5 from num1. Now the status bits are set. So we could say branch of 0 equals 5. Otherwise, I'll say not equal to 5. Well, if num1 is not equal to 5, what should I do? Set num2 equal to num1. So move ff num1 num2, or move num1 into 0 and then move wf num2, and then we're done. If the difference of our number and 5 was 0, then we jump down to equals 5, and what do we want to do? We want to clear num2, so clear file register num2, and then just fall through to done. All right, so main issue was doing things like, you know, forgetting this branch down here. So if num1 was not equal to 5, we'd set num2 equal to num1, and then we'd go ahead and we'd clear num2, right? So like always doing both conditions, both the then and the else. Other than that, it was minor things, minor opcode issues, things like that. So nothing too shocking there. And then question 6, we had 5 instructions to be executed sequentially. And I wanted you to write down, following each instruction, the contents of W, location 80, and location 81, using a question mark if those values are unknown. Okay, file registers are not automatically initialized to 0. If you want a 0 in a file register, you have to clear it. All right. So initially, all of these things have unknown values. So what are our instructions here? Move LW5, move W into file register 80, increment file register 80, decrement file register 80, and put the result into the W register, and then move file register 80 into file register 81. So let's just make a table. All right, move literal value 5 into W. What does that do? That sets the W register to 5. It has no effect on file register 80, so this is still unknown. It has no effect on register 81, so that's unknown. Move W into file register 80. Does not change the value of W, but it changes the value of file register 80 to be whatever W was. In other words, copy this 5 into here. 81 is still unknown. All right, increment file register 80 and do what with the result? There's no comma 0. Put the result back into file register 80. So read a 5, increment it as a 6, write it back into 80. This becomes a 6. This is still unknown. W has not changed. All right, decrement file register 80, but put the result back into the W register. That's what this comma 0 signifies. All right, read file register 80. That's a 6. Modify it by decrementing. That's a 5. Write the result back into the W register. This becomes a 5. File register 80 itself is not modified. 81 is still unknown. And then move file register 80 to file register 81. So take the contents of file register 80. Don't change it. Just copy it over to file register 81. So this becomes a 6. File register 80 is not changed, and the W register does not come into play in this. So that would be your answer for the last question. All right, questions on any of that?
So far, so good.
Awesome. All right, let's run through the homework. So I looked at questions 41 and 42, and these were using skip instructions. So x equals x minus 1. If x equals 0, go to somewhere. All right, well, x equals x minus 1, that's a decrement file register x. If we want to use a skip, there's a handy instruction called decrement file register and skip. So we can say decrement file register and skip if the result is 0, or decrement and skip if the result is not 0. Okay, skips will skip a single instruction. It's the immediately following instruction. So, and I always have a hard time with these opcodes. DCF SNZ. So there's the 2-line answer. Decrement file register X, that takes care of this. And if the result is not 0, skip this goto. But when we decrement, if the result is 0, we will not skip the next instruction, which means we'll execute the goto and we'll go to somewhere. So that bundles up this request that if x is equal to 0 after the decrement, go to somewhere. it's a little backwards feeling because we're seeing an if statement which says if x is equal to 0, but our opcode is the one that says not 0. And the same thing, if we want to do if x is not 0, go to somewhere, we're going to use a decrement file and skip if 0. So those can feel funny. And like I say, I usually ask people not to use skips on homework questions and such, but I want you to at least have seen them. Skips are actually really common on RISC processors, ARM processors, things like the PIC, and they're actually very efficient. They don't force you to flush the pipeline. They may skip one instruction, but your pipeline stays full, and so you maintain your efficiency. So skips are really popular on reduced instruction sets machines. And so, you know, in the field, you want to be able to use these things. But for now, I want you to learn and understand and be comfortable with program flow and conditional branches and status bits and so on. So we're using those to do our if statements. All right, question 51. Most people were pretty close on this, if not exact. Org 0x80, call sub. Org 100, there's our label sub. Increment file register 80, return. Okay, show the stack pointer and top of stack after each instruction. Okay, this is not an instruction. Does not execute. It's saying that this call should go at location 80 in memory. So I'm going to make a little program map. And I'm going to note where each of these instructions sits in memory. My call sits at location 80. My next instruction will be at location 84. How do I know that? Because a call takes 4 bytes. How do I know that? Table 20-1. Look up a call instruction. It's 32 bits. That's 4 bytes. So the address in program memory for the call starts at 80. The next instruction is going to be at 84. I didn't specify an instruction, but whatever the next instruction is, it's going to be at location 84. Now I say origin 100, so I'm going to jump down to location 100. And at that point, I'm going to find increment file register 80. Increment takes 2 bytes, so the next instruction is at location 102, and that's the return. Okay, so what's the initial stack? It's a bunch of question marks. Stack pointer is equal to 0, top of stack is unknown. If you did 0 for top of stack, that was okay. But technically it's unknown. Okay, when you say call sub, what happens? The address of the next instruction is pushed onto the stack. The next instruction is at address 84, so the top of the stack is going to get 84. Stack pointer is going to be equal to 1. Top of stack is going to be 84. Okay, why is it doing this? It's not just to have something to do. It's doing this because eventually we're going to say return, and we need to know where to return to. Now if I push an 80 on the stack and I say return, what's it going to do? It's going to come back here and it's going to say call sub. Or maybe if it's really smart, it's going to say, okay, I'm returning to the instruction from which I was called. It's going to have to interpret that and skip forward 4 bytes and then get down to an 84. But when we're executing call sub, the processor already knows the address of the next instruction. It's already figured it out. It's added 4 to the PC. It's got 84. Why not just push that on the stack? And then return, just pop the stack, jump there. Alright, so we call sub, this is what the stack looks like. This is also what the stack looks like when we say increment file register. Because increment file register does not affect the stack. Org does not affect the stack. Clear file register, add WF, move literal, none of these things affect the stack. Branch, go to, no effect. It's really just call, return, push, pop, retfee. I think that's it. And interrupts. Alright, so eventually we get to the return statement. So this is what the stack looks like after increment file register. After we say return, well, the top of the stack will still have a 0x84. These will be question marks. But the stack pointer will be equal to 0. And top of stack is probably going to be 0. But technically it's undefined. I didn't take off points for whatever you put on that. But I wanted to see, after each of these instructions, what the stack looks like, what the stack pointer is, what the top of the stack is. And some people indicated their stack pointer like this. And that's okay too, but I want you to think about the value of the stack pointer. It's a register, right? It's an 8-bit register with a value from 0 to 31. And it's really telling you how many things are on the stack. So the 0 here means the stack is empty. The 1 here means there's one thing on the stack. Alright, and in 52, same basic drill except we're using pushes and pops. So we started location 40. We have an increment file register for no reason, and then a pair of pushes and a pop. Alright, if I were to assemble this code in MPLAB and then look at the disassembly listing, I can figure out what the address of each of these instructions is. Okay, but I can also do this just by looking at the fact that I'm starting at origin 40, which means the next instruction will be at location 40. Increment takes 2 bytes, so this is at 42. Push takes 2 bytes, so this is at 44. Push takes 2 bytes, so this is at 46. Whatever comes after this would be at location 48. So sometimes you'll hear me talk about the PC or the address of an instruction. We're not talking about the file register. We're talking about where this instruction is stored in memory. Right? But I tried to avoid that language on the test. But make yourself a memory map if you want. Right? Or if you're, in the field, assemble this and look at this assembly listing. Alright, so same thing. What's the stack pointer look like initially? It's a bunch of unknowns. Stack pointer is 0, top of stack is unknown. So that's the initial value. That's also the value after the increment file register. Okay, what happens when we execute push? So this is the first push. We're going to push the address of the next instruction onto the stack. We're executing this instruction. What's the address of the next instruction? 44. So we push a 44 onto the stack. These are unknown. The stack pointer will change to 1, saying there's one thing on the stack, and top of stack will be 44. The second push well, we had a 0x44 here. The second push says push the address of the next instruction. The next instruction is at 46. So we're going to push a 46, which means write it at the address of the stack pointer, right, index 1, increment the stack pointer to say there's 2 things, and set the top of the stack to the thing that's at the top of the stack. That's at 46. And I want you to think about the fact that whether this was a pop or a call or a go-to or a no-op or an illegal opcode, the address of this instruction is still hex 46. It doesn't really matter what this instruction is. If I say push, it's guaranteed to push a 46. if I've never specified an instruction here, it'll still push a 46. Alright, and then when we do the pop, here's our stack. So that's a 44, that's a 46, these are unknown. When we pop, the stack pointer is decremented, and the top of the stack is the thing at the index of the stack pointer, so it's 44. So that's playing around with stacks. Alright, and then the other questions I looked at were 56 and 57. And I want to play with these in MPLAB after a break. But let me give you the basics here. So 56, we're trying to set up int 0 to generate interrupts. And every time you get an interrupt, you want to increment file register 2. Alright, so you need to set up. So let me make something like a flow chart for this. So I'm going to say here's what int 0 does. Increment file register 2. Clear the interrupt flag and then return from the interrupt. And our main program is going to set up the I/O subsystem, set up our interrupts, and then it's really just going to sit in a loop. Just going to branch to itself, because I don't think it says to do anything else. Alright, so how do we set up? We'll put a 7F into ADCON1. We don't really need to do that because we're not doing any I/O except for int 0 is an input, right? We need to make sure that we can read from bit 0 of port B, right? So back to your data sheet. Int 0, pin 8, that's also RB0. It's also analog input 4. So even though we're not explicitly reading bit values, we're trying to do input on this pin, which is also available for analog. So we need to put 7F into ADCON1, right? And again, you know, until we start doing analog stuff, just always put 7F into ADCON1. It can be your signature. So 7F into ADCON1. Well, by default, TRISC-B is all ones. So the default is that this will be set up as an input pin. How do you know that? Come up here to your table in your datasheet summary, look for tri-state B. Yeah, I should know where this is. So tri-state B, data control, register for port B. This shows you the initial values, right? So this is value on power on reset or brownout reset. So when you first turn it on, those bits are all set to 1, which means port B by default is all inputs. So you can bit set F tri-state B, comma 0 to explicitly set it to an input, or if you know it defaults to inputs, you can just run with that. So the main thing is the interrupt setup. Alright, so 7F into ADCON1. Go into the RCON register and set the interrupt priority enable bit. We don't need that because we're only doing one interrupt and we can just use it as high priority. Habits are good. Habits are what make us successful as a species. Build habits, right? And then you have to think less. Okay, maybe sometimes habits aren't good. But for assembly language programming, habits are good. So I always set archon bit 7 to a 1, right? But I just call it IPEN. It's the interrupt priority enable. And then I want to enable int 0 interrupts. And I already know that's in the intcon register. So that's int 0 interrupt enable. If you want to avoid a bogus interrupt in the beginning, let's clear the interrupt flag. So we clear the interrupt flag. And then we need to enable interrupts at a global level. So here we say bit set file register intcon global interrupt enable high. And now the interrupt system is armed. Okay, this says priority levels are recognized. This says I want int 0 to be able to request an interrupt. This clears the interrupt request flag if it was already set because of a prior pulse on the pin. And this says allow interrupts that are properly requested. Okay, that's the global interrupt enable. And now we can just sit here and just spin. That's this loop down here. You just hang out, wait for something to happen. Alright, where does all of this go in memory? You need a memory map. So program memory. Well, I'll just show you in the data sheet. So if you go up here, maybe I didn't put it in, or maybe I went by too quickly. Nope, I didn't put it in. Alright, well it's in the book anyway, but I'll draw you a picture. So location 0, that's the reset vector. Fancy way of saying when you power on the chip, that's where the processor goes, is location 8. Is location 0. Location 8, that's where you go when you have a high priority interrupt. Location 18, that's where you go when you have a low priority interrupt. Those are hardwired in the circuitry of the chip. So I need to start writing my code at location 0 because that's where I go on a reset. But if I put all this code at location 0, this is going to be at location 0, 2, 4, 6, this is going to be at location 8. That's where I need to put my interrupt code. So what do? We start off at location 0 and we say, let's just go to our main program. And then at location 8, we say let's go to our high priority code. And if we had low priority code, we could put a org 18 and say go to our low. Okay. Now I'm just going to put some code that's somewhere past, location 18. This is habit, right? In fact, I could just put my interrupt code at location 8 and then I could just fall into my main program and that'll work fine. But if I decide I want to add a low priority interrupt, I have to remember that that's what I did and move things around. So I'm going to do the same thing every time. Starting my program, I'm going to branch to a main. Location 8, I'll branch to a high priority code. 18, I'll branch to a low priority code if I have one. And then I'll just start off, somewhere past all of that foolishness. Start at location 20. That's where my main program will go. And so we set up ADCON, we set up the interrupt registers, we sit there and we spin. So eventually I have this spin. Go to spin. Well, I can put my high priority code here if I want. I could put it before main and after 20. I could put it explicitly somewhere else. It doesn't matter because I'm going to get here from a branch when I get my interrupt. Okay, so what do I want to do in my interrupt code? I want to increment file register 8. or file register 2. I want to clear the interrupt flag, so bit clear file register int con int 0 interrupt flag, and then I want to return from interrupt. Alright, so things that I saw here in the homework, aside from issues with the setup, make sure you clear the interrupt flag. If you don't clear that, the interrupt is still being requested. Okay, when you pulse pin 8 int 0, it sets a flip-flop. That flip-flop is int 0 IF. And if I don't clear that, when I return from interrupts, bang, I'm going to get another interrupt request. And I'm just going to keep getting int 0 interrupts. So clear that flag, but that's all you have to do. You do not need to re-enable int 0 IE, because that doesn't change when you get an interrupt. If you set that, that'll stay set forever. So you don't need to change that. You don't need to reset this. If you set that, that's set forever. You do not want to set this. Okay, the ret fee, sorry, this. The ret fee will set the global interrupt enable high. If you set that yourself in here, you're re-enabling interrupts while you're inside an interrupt routine, and that's really dangerous. Because as soon as you enable interrupts, you can get interrupted, and you might get interrupted before you return. You jump to location 8 again with a call, you come down here, you re-enable interrupts, you get another interrupt to location 8, and so on. You can blow up your stack. So don't do this, don't do that, just do this part. Right? You don't need to change ADCON 1, you don't need to deal with TRISB or anything like that. Just clear the interrupt flag, and then do your ret fee. Alright, 57, small change to that. You want to use pin 17 and you want to interrupt on the falling edge. So back to your data sheet, look at pin 17, that's int 2. Alright, so you want to interrupt on the falling edge of int 2. Other than that, everything's going to be the same. So go back, look at your registers. You're still going to want to set up IPEN in the ARCON register to allow priority levels. But for int 2, you need to look at the int con 3 register. And this is where the int 2 interrupt enable bit is, and the int 2 interrupt flag. The interrupt priority level defaults to a 1, that's what this -1 tells you, which means this is high priority to begin with. So you can use the same code, you can jump to location 8 when you get an int 2 interrupt. But we do need to change which edge you interrupt on, and that's in the int con 2 register. So we want interrupt edge 2, which we're told controls the edge for the interrupt 2. And the default value is 1, which means interrupt on the rising edge. Well, the question says interrupt on the falling edge, so we need to clear this bit. So bit clear file register int con 2, comma, int edge 2. That's the magic you need to make it interrupt on the falling edge. And then everything else is pretty much the same, except your interrupt enable and interrupt flag are in int con 3. But it's the same code. If you change it to be a low priority interrupt, right, by clearing this bit into interrupt priority, then your vector would be location 18. And so I would want to put this interrupt code at location 18 instead of 8. So that would be an org 18. Alright, so that was the homework. I tried to give you feedback on that. Alright, questions on Lab 4. And I'll get those graded. I may not get those graded by Thursday because I have a movie night tomorrow. But I'll get them graded in the next few days and I'll give you feedback. But any burning questions on Lab 4? Alright, let's take a 5-minute break. Let's come back at like 1:25. And I want to look at interrupts inside MPLAB, and then I want to look at timers inside MPLAB, and then I want to talk about Lab 5. All right, it's take about 5 minutes. We'll come back. We'll jump into the simulator and start doing some super low level debugging and analysis. All right, so I'll be back. So questions that came up in chat when we were going through the first half. So explain the k-bits again. So the k-bits are literally the bit value that you want to move into a register, for example. So if you're saying move LW, this bit pattern, it means take this bit pattern and load it into W. Right? So depending on what you're trying to move, or AND or XOR, the thing that you want to work with, the literal value, that's what those K's are in the instruction. That's what will get filled in these 8 bits. Can we just increment num with an incf? So I don't remember what question this was around, but if you're trying to do something like num equals num plus 1, right, that totally codes as an increment file register num. But if you're trying to do num equals 1, that's not necessarily the same as an increment. You can use increment only if you are absolutely sure that num is currently equal to 0. Otherwise, you would need to clear num and then increment it. Okay, but if you don't know the current value of num, the only way to increment it is with an increment file instruction. And chances are, if you were a compiler and you were asked to increment, to set num equal to 1, you would not generate code to clear num first. Because if this was a special function register and you cleared it, that might actually do something weird. So this can get into weird areas. Is there a high-level C code equivalent to a skip instruction to avoid flushing the pipeline? Usually not something that you can explicitly specify, but a good C compiler will be written for the specific architecture that you're compiling to, and it will know about things like skip instructions, the pipeline depth, the things that cause pipeline flushes, and it will compile code taking those things into account if it's a good C compiler. If it's a generic C compiler, it's probably not going to take advantage of those things. But a really good optimizing compiler, with the right switches when you invoke it, will probably do things like say, let's go to skip here, or let's go to skip if 0 or not 0 based on which condition is more likely, and so on and so forth. Yeah, you can get into all kinds of tricks like that. Compiler design is a whole art form. And it's one of these things where you think you're writing software, but you're really doing a lot of hardware engineering too. So that's an interesting area. All right, how does priority work? I understand that high priority goes to 8, low goes to 18, but how does priority demonstrate more urgency than low interrupts? The main thing with priority is that if you are processing a low priority interrupt, you can get interrupted by a high priority event. So you're doing your main program, and something low priority happens. You jump to location 18, and you're doing something. And all of something urgent happens, something that's high priority, you can get interrupted from here and go to location 8. Process that very important high priority event, then when you're done, come back here, finish your low priority, come back here to your main program. If, on the other hand, you're running your main program, doing your business, high priority event occurs, you jump to location 8, you're executing that. Let's say a low priority interrupt comes in, you will not be interrupted. You will continue with your high priority code until you say retfee, and then you'll go back and you'll immediately go to your low priority code. And then when that's done, you'll go back. So a high priority interrupt can interrupt low priority code, but not the other way around. So that's the real difference in the interrupts. If they both occur at the same time, right, it's possible that you'll jump to your low priority code first, but then you'll immediately get interrupted and jump to your high priority code. All right, and then last question, which also came up in email, I believe. Can you go over having 2 high priority interrupts like in Lab 4? So if there's two high priority interrupts that both come from the same pin, not necessarily. So you have three sources of interrupts in lab 4. You have int 0, int 1, and int 2. Alright, so three sources of interrupts. And they each come on their own pin. So int 0, int 1, and int 2. And I think this is pin 8, pin 9, and pin, I was going to say 17, but I think it's 18. Nope, it's 17. So pin 8, pin 9, and pin 17. If you don't do anything, these are all high priority interrupts. That's the I think that's the default. Okay, independent of the priority of these things, this is fired by, a rising edge on pin 8, this is fired by a rising edge on pin 9, this is a rising edge on pin 17. So these are independent interrupts, nothing to do with priorities. They could all be the same priority, and they would still be three separate events, right, from three separate pins. What you can do is you can use priority levels to differentiate between two groups of interrupts. For example, in our lab, we made these two high priority. So this is just for our lab. That was high, that was high, that was low. Okay, that means two things. One, when you get an int 2, you're going to jump to location 18, which means in your code at location 18, you got an interrupt 2. You don't have to do a lot of work. It also means that if you're inside your interrupt 2 handling code, and an int 0 or int 1 occurs, that will interrupt your interrupt code. And you'll jump into your location 8, deal with whichever pin was processed, and when you're done, you'll go back to finish up the interrupt 2 code, and then go back to your main program. The other effect is, whether you get int 0 or int 1, you're going to vector to location 8. And so how do you know which interrupt got you here? Well, this is where you check the interrupt flags. If int 0 IF is set, you know that int 0 fired. If int 1 IF is set, you know that int 1 fired. Both of those events will take you to location 8, but you can tell which interrupt occurred by checking these interrupt flags. And you can establish your own priority level between these two high events. If I check int 0 IF first, I'm giving int 0 higher priority. But if I were to check in my code int 1 IF before checking int 0, I'm giving int 1 higher priority, because I'm going to notice this interrupt request before I notice the int 0. So you can prioritize these things in software, but there is a very crude hardware prioritization, which is 2 levels, just high and low. So yeah, the signals come from different pins, which is what causes the different IFs to be set, int 0 IF or int 1 IF in this case. And then you look at those. So bigger machines will have more priority levels. So the VAX had like 31 different priority levels for interrupts. Some processors only have a single priority level. And that's okay. It just means anytime anything requests an interrupt, you end up at the same location, and then you have to decide, by looking at the flags, who asked for the interrupt. Alright, so I think that was it for chat questions that came in while I wasn't looking at my chat window. And I got my second one up, so if you have chat questions, post them on the second version of me. Alright, let's play with MPLAB. Actually, I want to do one other thing too. we go over the registers that change the system clock? The one from Thursday. Let's see, changing the system clock. So are we talking about timer 0? Well, I'm going to go through timer 0 after we play with some interrupts. And if that's not what you're asking about, send me another message and let me know. Alright, I'm going to close this. Alright, yeah, we'll play with timer 0 after this. If you want to use int 0, 1, or 2, you do have to set the first 3 bits of tri-state B accordingly. But remember those default to inputs also. But yeah, those have to be input pins in order to receive interrupt requests on them. That was a question from someone. Alright, let's write some code. So this is boilerplate stuff so far, right? This is just kind of our standard setup when we're playing with interrupts. We're always going to want to do these kinds of things. Alright, so we're going to play with interrupt pin 0. So what do we need to do? Bit set archon, IPen to allow priority levels. So we'll enable interrupt 0 interrupts. So that's int 0 IE. This is kind of optional, but you know, if something accidentally bumped pin 8 on my PIC chip while I was powering up, I may already have an interrupt request coming in, so I'm just going to clear that, right? So I'm going to clear that interrupt flag, and I'm going to turn on interrupts. And I'm going to set the bit called global interrupt enable high, GIEH. That's bit 7 of intcon. That turns on interrupts at a global level. At that point, my system is armed, which means from this point forward, I could get interrupted. All right. So what am I going to do? I'm going to make a loop. With no particular business going on in there. Alright, I need my high priority code. And what am I going to do? I'm going to let's just toggle bit 0 of port A, which means in my setup I'm going to clear bit 0 of tri-state A, which will allow output on port A, bit 0. And so when I get an interrupt, I'm going to toggle that. I'm going to clear the interrupt flag, and I'm going to rectify. That's my whole program. Alright, I'm going to put a breakpoint down here. I'm going to put a breakpoint at my high priority interrupt code. And I'm going to make a stimulus pin. So int 0 is RB0. So I'll put a stimulus on RB0. And I'm going to set the action to pulse high. So when I hit this, pin 8 of the chip will go high for one cycle, and then it'll go low again. So a student showed me this last week. So it's a lot easier than toggling or having a pair of pulses to go high and then low. Alright, so I have a breakpoint at my high code. Let's go ahead and build this. Let's go ahead and run this.
Can you put the breakpoint at 25?
Oh yeah, I need the breakpoint somewhere real. Alright. Thank you. Alright, let's build that. Let's go ahead and run it. Let's look at our variables. And down here I've got the little Cylon eyeball going back and forth. It means my program is running. Now I can pause it, and I'm sitting right here where it says go to loop, and I can single step, right? But that's all that's happening, right? And for the people who normally chime out at 1:50, I'm planning to go until about 2:15 today, so stick around if you can. So I'm just going to let this thing free run, right? And it's just running, it's running, it's running. That's all it's ever going to do. But I have interrupts armed. So when I say let's pulse RB0, suddenly the processor halts, the debugger halts, because it has jumped down to my high priority code. And what I'm going to do here is I'm going to toggle bit 0 of port A. So port A is all zeros right now when I execute that instruction. You can see that low bit turned into a 1. I'm going to clear the file register that's interrupt flag. Well, here's the value of intcon right now. I'm going to clear the interrupt flag so you can see it change to this value. And then I'm going to retfee, and retfee will take me back into my loop where I happen to be. And if I single step this, let's go ahead and fire our interrupt request again. And the next instruction should be my go-to loop. Well, it is, right? The instruction after that should be my no-op at loop, but at this point, my interrupt kicks in and I jump to location 8. And that says go to high pri. That says toggle bit 0 of port A, so that becomes a 0. Clear the interrupt flag, and then go back and retfee, and now I'm at the loop statement that I was going to. And I'll stay here in this loop. Okay, so we can hover over, say, the word intcon, and we can see a nice picture of what all these bits are. You can see int 0 IE, that's bit 4, is set to a 1. Global interrupt enable high, bit 7 is set to a 1. RBIF is set to a 1. Well, we're not using port B interrupts explicitly. So that's kind of a red herring. But let's see what happens when I fire this pin. So look at my intcon value. It's 1001 and then 0001. So all that's set in here right now is global interrupt enable and int 0 interrupt enable. Let's fire an interrupt request. Now intcon hasn't changed yet. Okay, it's still got those values. Let's step forward 1 clock cycle. And if you look at intcon, there's a new bit set, bit 1, int 0 interrupt flag. That's what gets set when you fire the int 0 pin. It turns on that IF flip-flop. If that is a 1, and if int 0 IE is a 1, and if global interrupt enable high is a 1, then you will get an interrupt. So all of those 3 bits are 1, so when I step one more spot, suddenly I'm back at location 8. And if I look at intcon right now, bit 7 turned to a 0. The processor does that for you. It disables your global high priority interrupts when you're processing an interrupt. Now, if this was a low priority interrupt, then that global interrupt enable high bit would still be a 1. But since this is a high priority interrupt, that bit gets cleared to a 0. And so I have the interrupt flag turned on, that's bit 1, and I have the interrupt enable for int 0, that's bit 4, but the global interrupts got disabled. And if I fire this pin again, right, it's not going to change anything. It's not going to trigger an interrupt because I don't have global interrupts enabled. Now I can come in here and I can mess with the system and I can change this to a 93. And what have I done? Well, I've just snuck into the mind of the processor and I've turned global interrupt enables on, global interrupts on. Right, bit 7, global interrupt enable high. Well, I'm about to say go to high pri, so I do that, and I'm about to toggle bit 0 of port A, but guess what? The processor noticed that I had an interrupt request, high priority interrupts were enabled, it jumped back to location 8. Okay, so when you get an interrupt, interrupts at that level or lower are disabled to prevent you from getting, repeatedly interrupted inside your interrupt code. And if you turn that interrupt enable back on in your code, you run this risk of getting nested interrupts. Alright, so those interrupt flags get cleared for you by the processor, and they'll get reset to 1 when you do the ret fee. So let's toggle port A, let's clear the interrupt flag, and we're ready to do a ret fee. So the interrupt flag is off, that's bit 1. The ret fee will turn on global interrupt enable high. Right, so global interrupt enable high is turned on now. And this was where I was when I went in and tweaked the intcon register. Right, so we're in the middle of our interrupted interrupt code, and eventually it'll return and go back to the loop. So you can play around with this stuff inside the simulator. You can see exactly what's happening when you fire interrupts, and if you have multiple interrupts, this is a really good way to play around with it. If we were to fire a low priority interrupt, we would jump to location 18, we could start stepping through that and then fire a high priority interrupt. We would see that previous code get interrupted and we would vector to location 8. And then when we ret feed, eventually we'd go back to our low priority code, and then when that hit its ret fee, it would go back to our main program. Alright, let's play around with timers. So let's look at our registers really quickly. So I'm going to stick with timer 0 for now, and I think we'll get into the other timers on Thursday. But timer 0 interrupt flag and timer 0 interrupt enable are both in intcon. Alright, so I can kind of stay where I was. So we'll keep this code up here the same. I don't know if we need output on port A, but that's okay. So we'll allow priority levels. We'll allow timer 0 interrupts. We'll clear any pending interrupts, and then we'll turn on global interrupts. So that should arm the system to do timer 0 interrupts. First we have to set up timer 0. So we have to play with this timer 0 configuration register. So T0 con. Alright, T0 con, what do we want to do? We're going to turn it on, so bit 7 is going to be a 1. Alright, that's what turns on the timer. Let's just do 8-bit timing registers. We'll keep it simple for now. So timer 0 is configured as an 8-bit timer. So we'll set bit 6 to a 1. We're going to interrupt on the instruction clock. Okay, we're not going to use an external pin. So we'll set bit 5 to a 0. Doesn't matter whether we do the high edge or the low edge because we're not interrupting on a pin, so I'll just leave that as a 0. And let's not do a prescaler. Okay, so let's do prescaler not assigned. That means bit 3 should be a 1, and then bits 2 through 0 don't matter. So we're going to set T0 con to be this. Alright, so this bit pattern says turn the timer on, use 8-bit counting, increment on the instruction cycle clock, and don't have a prescaler. And there's no way to know any of that unless you look at the data sheet. Okay, and if we wanted something different, we would have a different pattern that we'd be moving into T0 con. Alright, let's set up a delay. So we're going to use this register called timer 0L. That's the lower 8 bits of the timer 0 register. Remember, if we're doing 16-bit counting, we have timer 0 high and timer 0L, and they together form a 16-bit register. We're just going to do 8 bits, so we're just going to deal with this timer 0L. And remember, the way this works is we load some initial value into here, and it will increment up until it overflows, and when it overflows, we'll get an interrupt request. That's the whole setup. So let's put a value into here. So let's move 246 into the W register. And let's put that in the timer 0 register. Which should request an interrupt after 10 increments or 10 clock cycles. And then we'll turn on interrupts and we'll just go into our loop and hang out here. And let me make my loop. Some more no-ops just for fun. Alright, so I'm going to look at my timer 0L register. I'm not going to need my stimulus window. But I might look at my stopwatch. I don't think I need my stopwatch. Alright, so I'm going to put a breakpoint right here at this interrupt enable. So I'm going to build this, I'm going to run it, I'm going to come in and look at my variables. Alright, so timer 0L is set to the value 246. Port A we're not using, that's okay. Let's start stepping this code. Let me go ahead and put intcon 0 on here. Intcon. Alright, and so intcon, we've got timer 0 interrupt enabled, and that's it. Okay, we're going to turn on global interrupts. So I'm going to step through this one instruction, and a couple of things are going to happen. Number one, intcon is going to change. Okay, that most significant bit which is global interrupt enable high, is going to change to a 1. But I want you to look at the value of timer 0L, which is 246 right now. Watch what happens when I step forward one instruction. Oh, that was boring. Oh, that might be a glitch. Okay, well, bit 7 got turned on in intcon. That's good. Let's step forward again. Okay. It took a few cycles, but anyway, timer 0L just incremented to 247. And if I step again, it'll increment to 248. And when I step to the next instruction, it increments to 249. Right? Every time I execute an instruction, this register is going up by 1. That's that basic core mechanism of the timers. Execute an instruction, that's the instruction cycle clock. We're saying increment the timer register. So it's 251, 2, 3, 4, 5. What's going to happen on my next instruction? This register is going to increment once more, which is going to roll over from 255 to 0. And guess what? My intcon register also changed. In particular, timer 0 interrupt flag just changed to a 1. That's bit 2. Right? Why did that happen? Because timer 0L overflowed. It rolled over from 255 to 0. So the timer is now requesting an interrupt. And it'll take a cycle or two to kick in. And it jumps down to location 8, and that says go to the high priority code, and that says bit toggle bit 0 of port A, and port A just changed. And now we're going to clear the interrupt flag, and we're going to do a ret fee. Look at the value of timer 0L. It's a 7 already, right? It rolled over to 0, but every time the instruction cycle ticks, this value gets incremented. So now it's at an 11. Why? Because those branches take times to execute. The return from instruction takes more than one cycle. So now we're up to location 11. We're up to a value of 11. And we're getting another interrupt request. And we're getting an interrupt request because timer 0 interrupt flag is set to 1. Does everybody see the problem? So here's the action. We do a return from interrupt.
Go
ahead.
You didn't clear the timer flag.
I didn't clear the timer flag, right? So if you're running your code on a proto board, right, it might look like it's doing the right thing, but if you're single stepping it, it jumps out at you. As soon as I come back from the interrupt, I'm back in my interrupt code. Why is that? Well, I should be clearing the interrupt right here, so double check. Look at your interrupt register. Yep, the interrupt flag is set. Let's go ahead and clear that bit. And let's look at the interrupt register now. And you can very clearly see timer 0 interrupt flag is still turned on. Right? So there's your big hint that I messed up. Right? I should have cleared timer 0 interrupt flag. Okay, well, not a big deal. Stop, rebuild, run, and we're back and running. So look at your variables and start stepping through. And we're about to increment timer 0 from 255 to 256. That generates an interrupt request. We go to location 8. Our timer is continuing to increment. It's already incremented back to 3. We're going to say go to high pri. That takes 2 cycles, so the timer is equal to 5 now. We'll toggle port A. We'll bit clear the file register. Timer 0 is now 7. We're going to do the ret fee. And ret fee takes 2 instructions, so now timer 0 is a 9, and we're back in our loop. Go-to is going to take 2 cycles, so it jumps to 11. No-op takes 1 cycle, so it goes to 12, 13, 14, 15. And this will just keep going until eventually it overflows again. So if I just let this thing free run, I have a breakpoint set in my high priority code. right? And timer 0 overflowed. It got a few cycles beyond. It jumped to location 8. It did go to high pry. Now it's equal to 5. All right, so what are we doing? Number one, we're watching this thing as it runs, right? And we're seeing how these values are changing. Number two, we're seeing a problem with our code. If we wanted to interrupt every 10 cycles, this is not happening. The first time we did this, it took 10 instruction cycles to generate the interrupt. Why? Because we started with a value of 246. But after this register overflows, timer 0L, it's a 0. And it's going to take 256 cycles for it to overflow again. So typically what we're going to do in our code here is something like this. When you get your interrupt, reset your timer register. Right, so put a 246 into W, put that back into timer 0L. So let's try that. So the timer is 246, 247, 8, 9, 0, 1, 2, 3, 4, 5, 6, and we get the interrupt request. Alright, we go into our interrupt code, the timer starts incrementing again, right? It's up to 5. We reset it to 246. We toggled port A. We cleared the interrupt flag. We did our ret fee, and now we're going to sit in here for a few cycles. And then we're going to jump down to our interrupt code. Alright, so I have a breakpoint set here at this port A. If I just tell it to run until it hits a breakpoint, my stopwatch window here will tell me how much time has passed since the last breakpoint. Okay, normally it's just cumulative, but if you run and stop when you hit a breakpoint, it'll tell you how much time has passed. And it's telling me 19 seconds have passed since the last breakpoint, 19 instruction cycles. Okay, it's supposed to be 10, but there's wiggle room in here. But if I change this thing to start at 236 instead of 246, and I run this, it's taking 29 cycles. Right, now this value should interrupt every 20, but there's 9 cycles of overhead. If I set this to 200, it should interrupt every 56 instruction cycles, but it's actually taking 65. 56 plus 9 overhead. Now if I really wanted to interrupt every 56 microseconds, what would I do? I would take off 9 from this count. I would start at 9 closer. And now we're at 56 microseconds, I end up back in my interrupt code. Alright, so this is a super low level look at the timing subsystem. The video that I posted, the long boring one, right, is all about doing these kinds of things. Now I did it in that video on questions like question 4 from the midterm, where you're basically just manipulating file registers, comparing them, doing conditionals. But you can do exactly the same technique to look at the hardware subsystems, the interrupts, the timers, and the other things that we're going to be playing with the rest of this course. Okay, so that's totally worth doing. We've talked about how the timer works, how the timer register gets incremented, and so on and so forth. Let me show you one other version of this, and then we'll run through Lab 5 really quickly. Let's go back to our timer 0 configuration register. Suppose we wanted a prescaler. Suppose we wanted a 1 to 4 prescaler. Let's just do 1 to 2. Okay. The trick is make bit 3 a 0, just say use a prescaler, and then set these 3 bits to be 0. So we want to change our configuration register to this. And that'll give us a 1 to 2 prescaler. So I'm going to keep pretty much the same code, but I'm going to change this one bit to make a 1 to 2 prescaler. Everything else is exactly the same. So I'm going to rebuild that. I'm going to run that. And I'm going to look at my timer 0L. So I'm looking at this. Now let's jump down further. Alright, so timer 0L is 209. And let's come back into our main loop here. Okay, so timer 0L is 210. Instruction 211. Instruction 212. Go to takes 2 instructions. Okay, it's a 213, instruction 214, instruction 215, instruction 216. This is the essence of the prescaler. It takes 2 instructions before that register increments. Instruction 1, no change. Instruction 2, it goes to 218. So the prescaler is basically slowing down how quickly this register increments. That lets us have a longer timing period. If I set the prescaler to be 1 to 4, I would have to go click, 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 4 instructions before the register increments. Click, 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 it increments a second time. So you need more instructions to execute to increment the register. It's going to take longer for it to overflow. It's going to be longer before the interrupt request occurs. So the prescaler slows down how quickly that register gets incremented. That's the essence of the prescaler. Alright, so let's look really quickly at Lab 5. Or maybe not so quickly. I'm going to have to post a video on pulse width modulation. So I will make a video and I will post it later on today. But basically, you're going to write code that generates a waveform. And you're going to want to generate different kinds of waveforms. Sometimes you're going to generate a waveform like this. And sometimes you're going to generate a waveform like this. And other times you're going to generate a waveform like this. Okay, I'll post a video and I'll talk about this idea, which is called pulse width modulation. And the idea is the frequency of these 3 waveforms is the same. The number of times this pulse goes high and low in a certain period is exactly the same. But this is high half the time and low half the time. This is high very little of the time. It's mostly low. And this third waveform is mostly high. If I hook this up to a motor, the motor will spin very fast, because it's almost getting a constant voltage. If I hook this up to the same motor, it will spin very slowly. And if I hook this up to a motor, it will spin at about half the speed of this, because it's only getting the signal to turn half the time. And so even though computers only let us put out a binary value, either a 1 or a 0, 5 volts or 0 volts, we can do things like control the speed of a motor. Not by changing the voltage, but by changing how much power is delivered to it, basically. How long the signal is high versus how long it's low. That's pulse width modulation. So this lab is about doing pulse width modulation. And I'll post a video on what that means and how to interpret it, but here's what you're after. It's a single experiment. You're going to write code that generates a signal on RB0, and it changes every quarter of a second. Okay, 0.256 seconds. It should toggle. So that's constantly toggling back and forth. But while that's happening, every half second, you want to change what's happening on pin RA0. So pin RA0 should be outputting a signal that's going high and low, but you initially want to go high 100% of the time. So you want to generate a constant signal. And then after half a second, you want to drop down to 75% power, which means you want a waveform that's high 3/4 of the time.
So when you're referring to the percentage of power, is that the same thing at duty cycle, or?
That's the duty cycle. That's saying if it's 75%, it means I want it to be high 75% of the time.
Okay.
If I want 50% power, it should look like this. If I want 25% power, it should look like this. If I want 0 power, it should just be off. So you're doing a few things in here. Okay, you're constantly generating an output waveform on pin RA0. And the way that looks is going to change over time. Sometimes it'll be on 100% of the time. Sometimes it'll be on half the time, off half the time. Sometimes it'll be completely off, or mostly off, or mostly on. And you're going to move from one of these states to the next. You're going to go through all 9 states and then go back to the beginning. So if you hooked a motor up to this, what would happen is that the motor would spin very fast for half a second and then start to slow down, slow down, slow down, and after a few seconds it would stop, and then it would start slowly speeding up until it comes up to 100% power, and then it goes back and it repeats. So RA0 is constantly toggling, but the duty cycle, the appearance of it, how long it's on versus off, is changing every half second. And while all of that is happening, you want RB0 to be turning on and off every 1/4 of a second. So you can't just do this with delay loops. You can't just make a loop that decrements decount until it's 0 and so on and so forth. You have to do this using the timers. And one way to do this is to set up a timer which will interrupt you every 0.256 seconds, and then write some code that says, what should I do now? Okay, this is more state-driven code. And there's sample code to help you with this. Okay, so the sample code uses timer 0, counts from 0 to 65,535, toggles RA0 every 256 microseconds. So you've got the beginning of your code. Okay, it's toggling, you're supposed to toggle RB0 every 256. Well, this code toggles RA0 every 256 microseconds. So you're going to want to tweak it. But this is basically, you know, the usual startup stuff. Go to main, 8 goes to high priority, 20 is our main code. Don't worry about the oscillator configuration because that's kind of bogus for us. Enable low priority interrupts, enable timer 0 interrupts, set timer 0 to be high priority, that's the default, enable priority levels here, clear any pending interrupt flag, set up the configuration register, so they're using 8 bits, instruction clock, and a 1 to 4 prescaler. You may want to do something different. This is setting timer 0L to 0 initially, which means it'll take 256 ticks for it to turn on. And after this is all set up, the code is turning on bit 7 of timer 0 configuration, which is the on bit. And then enable global interrupts and just go into your main loop that just sits here and spins. When you get an interrupt, check to make sure it came from timer 0. That's really the only choice right now. So we'll jump down here. And this code is written to keep track of how many interrupts have occurred. So it increments this thing called least significant byte. And if it increments it to 0, it'll go ahead and increment the most significant byte. You don't need to do this. Okay, this is just demo code. And then it toggles bit 0 of port A, clears the interrupt flag, does a ret fee. So your biggest challenge in this code is really thinking about the algorithm. Think about an algorithm from a high-level point of view. How are you going to get this behavior out? But think about it from an interrupt-driven point of view. Suppose that every 0.256 seconds someone comes over and pokes you in the arm. How do you figure out what you should do? Should I toggle RA0? Should I toggle RB0? Should I go from one state to another? That's the real challenge of this. Alright, I'm going to hop into my office hours. Come by, ask questions about this. I will post a short video later on pulse width modulation, but we already kind of talked about it in general, but I'll put it in the video. Alright, I'll see you in office hours.